Let's talk about Newton's second law, which states that a net force is equal to mass multiplied by acceleration. And of course, the base SI units for mass and acceleration are kilograms and meters per second, respectively. Let's take a look at your equation sheet here. And highlighted, you'll see the exact same equation that I referenced when I taught you about Newton's first law, inertia, and inertial mass. So that states that acceleration, which is a vector quantity, is equal to the sum of the forces divided by mass, where the sum of the forces is the net force. And recall that the net force is the summation of all forces acting upon an object. Now, if we take this equation and rearrange it, we get Newton's second law. The sum of the forces equals mass times the acceleration. So all I've done here is multiplied both sides by mass, and there you have it. The acceleration is a vector, and it is in the same direction as force, which is also a vector. Let's look at the units for a Newton and the base SI units for a Newton. So force equals mass times acceleration. And you know that the unit for force is a Newton. That's a derived unit. Well, if you look here, what is a Newton expressed in base SI units? It's kilogram multiplied by meters per second. So essentially what this is saying is that 1 Newton is the force that is required to accelerate 1 kilogram of mass at a rate of 1 meter per second. Okay, so let's do a couple basic practice problems here. Neglecting friction, how much force must be applied to accelerate this 100 kilogram object 0.5 meters per second to the right? Guys, the first thing we need to do is we need to define our coordinate system and define our positive and negative directions. So typically, we will call to the right positive, to the left negative. We will call up positive and down negative, and indeed that is what we will do for this problem. However, there are times where we will call down positive and up negative, depending on the situation. So let's go ahead, as you learned in the previous video, and start with our free body diagram. So we have our vector quantities and our forces acting on this one object, the 100 kilogram object, and we're representing them by arrows starting on this dot and extending away from the dot, where the length of each arrow represents the relative magnitude of the force. So there are 3 forces acting on this object. 1 force to the right in the x direction and 2 forces, 1 up, 1 down in the y direction. Okay, so I'm going to be using a PHET simulation here, as you'll see that I'll use really throughout the course. I would always encourage you to hop online and go to this website and check it out yourself. So Newton's second law, the net force equals mass times acceleration. Let's go ahead and solve this problem. So we are talking about acceleration to the right, so that would be in the x direction. I have used a subscript of an x to denote that, just as we did in the previous unit of kinematics. There's 1 force acting in the x direction, which would be the force applied, the force of the man on the bucket of water, and that force is therefore equal to mass times the acceleration in the x direction. So now we can simply plug in our values and solve for the force applied. And we get that the force applied would be 50 newtons. And indeed, if I apply a 50 Newton force to this object, you can see that it now has begun to accelerate, and the acceleration is 0.5 meters per second. And so that 50 Newton force to the right has resulted in this 100 kilogram object accelerating at 0.5 meters per second to the right. Okay, now I want to now go ahead and consider some other questions, like what about the forces in the y direction? Those forces do exist, so let's go ahead and analyze them. So using Newton's second law and denoting that we're looking in the y direction with a subscript of y, and calling up positive and down negative, I have that the force in the y direction is equal to force normal, which is positive, minus the force of gravity. And that is equal to mass times the acceleration in the y direction. Now, in the next video, I'm going to speak to you more about summing the forces and some of the methodologies employed here. But for now, just up positive, down negative, so I'm subtracting my downward force of gravity from my upward force normal in this expression. Okay, now here's the big conceptual hurdle. This object is not and does not accelerate up or down. It has zero acceleration in the y direction. Now in the x direction, we saw it had 0.5 meters per second, but in the y, it's 0. So look at our expression here, guys. Check it out. What this means is that the net force in the y direction is therefore equal to 0 newtons. That's important. Let's look at another question here. A man applies a force of 263 newtons to the right. The force of friction is 188 newtons to the left. Calculate the acceleration of this 100 kilogram object, and we're going to leave the same defined coordinate system in positive and negative directions as we did in question 1. So we have force normal, force of gravity, force applied, and now we have the force of friction. Again, recall that the forces in the y direction sum to 0. In other words, the net force in the y direction is 0, which means force normal is equal in magnitude but opposite in direction to the force of gravity. When you add them together, they equal 0. Now also check out the free body diagram, and I want you to notice that the force applied has been shown to be greater in magnitude, i.e. the arrow, the vector arrow extending from the dot is longer than the force of friction, which implies this object will accelerate to the right, that there is a net force to the right, that these forces in the x direction are not balanced, which indeed we are explicitly told in this problem because we're trying to calculate the acceleration. All right, so let's go ahead and look at some of our numbers here. So Newton's second law, we're looking in the x direction. We're calling right positive, left negative, so I'm subtracting the force of friction from the force applied and setting that sum equal to mass times acceleration in the x direction. Plugging in our values of 263 and 188 newtons and the fact that this object has a mass of 100 kilograms, we can solve for the acceleration to be 0.75 meters per second, as you can see on the screen there. That is indeed the acceleration. If you go play around with this simulation on your own, you'll see this scenario holds true. Okay, so let's look at the units here. So for this expression, we divided newtons by kilogram. Okay, so what is a newton expressed in base SI units? Well, as I just went over, that would be a kilogram multiplied by meters per second. That's a newton. And we're dividing by kilograms because we divide by the 100 kilogram mass to solve for the acceleration. And it becomes readily apparent that kilograms cancels out, leaving you with the all familiar SI units for acceleration. what force must the man apply to double the acceleration of the same object on the same surface? So we're going to be using this mathematical reasoning as we will throughout the course. And in a previous video, we stated that the acceleration was directly proportional to the net force. Acceleration is directly proportional to the sum of the forces. If I double one, I double the other, because they are directly proportional. The only issue is here, guys, you need to pay attention. The sum of the forces need to double. So let's look at this problem. If he doubles the net force, again, underlined to accentuate the importance of understanding that, then the acceleration will also double. Well, in scenario 1, our net force was 75 newtons. That was the 263 minus the 188. Gave us a net force of 75 newtons. And that net force of 75 newtons resulted in the acceleration of 0.75 meters per second. Now, we want to double that. We want the acceleration to be equal to 1.5 meters per second. That means we need to double the net force. So let's look back at our summation when we sum the forces in part A of this problem. We took force applied, we subtracted the force of friction, and now we're going to say, instead of that equaling 75 newtons, it equals twice that. So 150 newtons is the net force. Now this problem is saying what force must the man apply? So we are solving for the force applied. Friction is not going to change. It's the same object on the same surface. And even though we haven't talked about kinetic and static friction, that's coming up, you have enough of an idea of what friction is to understand that. So if we look at this and we solve for the force applied, now what did I do here? I just added 188 newtons to both sides, and I get that if this man applies a force of 338 newtons to the right, this object will accelerate at twice the acceleration we had in part A. So in other words, 1.5 meters per second. And as you can see here with this simulation, and again, go on and do it yourself, you get with these exact numbers, here's the force applied to the right, and we did the physics to show that, 338 newtons, and that results in a 1.5 meters per second acceleration to the right, which was double the magnitude and double that of the initial acceleration. So in this video, we've begun to look at summing forces on objects. You've looked now at what Newton's second law is, you know what Newton's first law is, and so we're really beginning to analyze these forces. And I'll see you guys in class.